The cosmological principle relies on two distinct properties. The first is spatial homogeneity, which dictates that matter is distributed with a constant density. The second is isotropy, meaning the universe looks uniform in all viewing directions. This principle is a non-negotiable mathematical requirement for the Friedmann-Lemaitre-Robertson-Walker metric. When Georges Lemaitre and others derived the equations governing the expanding universe, they required a uniform distribution of matter for the math to function. We know the universe is highly clustered on small scales into galaxies and local groups. To apply the metric, we have to zoom out to a scale where this localized clustering smooths out into a uniform fluid. This 3D grid models that transition. Astrophysicists like Jaswant Yadav ran n-body simulations to find the exact threshold for this end of greatness. They calculated that statistical homogeneity must emerge at scales larger than 260 over h megaparsecs. Confirming this limit is an existential requirement for the lambda cold dark matter model. If the universe remains clumped at scales larger than this threshold, the equations governing cosmic expansion lose their physical foundation. Deep sky spectroscopic surveys have removed the guesswork from these scales, mapping the exact three-dimensional coordinates of galaxies with unprecedented precision. In 2016, utilizing data from the Sloan Digital Sky Survey, researcher Heidi Lietzen and her team identified the Boss Great Wall. Located at a mean redshift of 0.47, this superstructure complex spans a physical diameter of roughly 1 billion light-years. A physical diameter exceeding 300 megaparsecs stands in direct contrast to the 260 over h megaparsec limit, where homogeneity is mathematically required to begin. The observation of this megastructure demotes the cosmological principle from an absolute theoretical law to a highly vulnerable, testable hypothesis. The Sloan Digital Sky Survey's Baryon Oscillation Spectroscopic Survey, or BOSS, gathered a dataset of over 1 million galaxies to reach these depths. The project was designed to measure baryon acoustic oscillations. These are the frozen imprints of sound waves that propagated through the ultra-hot plasma of the early universe. This primordial acoustic wave expands and freezes at recombination, leaving a 150 megaparsec spherical ring of denser galaxy distribution. This ring acts as a standard cosmological ruler, used by astrophysicists to measure angular diameter distance and expansion rate at specific redshifts. Precisely charting galaxy positions to locate these acoustic rings had an unintended consequence. It produced a high-definition map of the cosmic web itself. The Boss Great Wall stands as a massive physical obstacle, mapped by the very same high-precision tools designed to confirm dark energy. This Brie-B Cartesian plot breaks down the morphology of the Boss Great Wall into 4 primary superclusters, A, B, C, and D. The structure features 2 elongated galaxy walls. Supercluster A spans 186 over h megaparsecs, and supercluster B reaches 173. The complex contains at least 830 visible, high stellar mass galaxies, resulting in a total mass approximately 10,000 times that of the Milky Way. To verify these dimensions, researchers applied Minkowski functionals, a set of topological mathematics used to quantify a structure's thickness, width, length, and overall curvature. The research team compared these Minkowski metrics against known local superclusters in the Sloan Digital Sky Survey's 7th data release to confirm the wall's anomalous Dulles density. Applying Minkowski functionals strips away the possibility of an optical illusion. The Boss Great Wall is a distinct, verified morphological giant. The standard model maintains a statistical defense. Finding contiguous overdensities does not strictly violate homogeneity, provided those overdensities are just transient phenomena. For a collection of galaxies to be classified as a true, singular structure, it must be in mechanical equilibrium. Its gravity must pull inward toward a shared center of mass, resisting the stretching of the background space. We have to differentiate between a gravitationally bound complex moving together and a spatial coincidence that is being slowly torn apart by Hubble expansion. The current empirical limitation is distance. At a redshift of 0.47, astrophysicists cannot measure mechanical equilibrium parallel to the line of sight. If the Great Wall is slowly dissolving, the metric survives. If it is mechanically bound, the standard model faces a structural crisis. If the Boss Great Wall was the only anomaly, it could be dismissed as a statistical fluke. Subsequent observations have expanded the catalog. Sloan Great Wall measures 423 megaparsecs. Huge, Large Quasar Group measures 780. This radar plot maps the footprints of extreme recent discoveries. The giant arc spans 1,000 megaparsecs, and the Big Ring reaches 1.3 billion light-years. Both completely engulf the 260/h megaparsec limit for homogeneity shown in the center. The increasing frequency of these discoveries systematically dismantles the statistical outlier descents. The math dictating the scale of homogeneity is breaking under the weight of observation. Spatial structures are not the only localized anomalies. Cosmologists also face the Hubble constant tension. The local expansion rate from Cepheids and supernovae yields 73.24 kilometers per second per megaparsec. The early universe measurement from Planck sits lower, at 66.93. The cosmic microwave background presents its own deviations, specifically hemispheric biases and a pronounced temperature dipole. Astrophysicists debate whether the CMB dipole is purely kinematic, caused by our solar system's motion, or if it signals an intrinsic anisotropy in the universe. Between a billion light-year megastructure, a disputed expansion rate, and a lopsided microwave background, the Standard Model faces simultaneous crises on multiple fronts. The foundational cosmological principle remains in place, though the scale at which the universe plays fair with our math must be vastly larger than 260/h megaparsecs. Future high-redshift spectroscopic surveys must map the cosmic web far beyond a redshift of 1 to find the true end of greatness. We must either find the boundary of homogeneity soon, or accept that we live in an intrinsically inhomogeneous, lopsided universe where the foundational metric is obsolete.